Okay, now let's talk about section 3, zeros of analytic functions. We just proved in a small neighborhood an analytic function has the power series expansion in a small neighborhood for some sufficiently small radius. So in other words, analytic function can be considered as an infinite polynomial. Well, it's just a very rough idea, infinite polynomial. So we want to see what kind of a property of a polynomial can be extended. What property of polynomials can be extended to analytic functions? Right? That's a very natural idea or question, because this is like infinite order. For the polynomial, we have division. If we have a polynomial, and q is another polynomial, then you divide p by q, you will have s the quotient plus r the remainder, the division, right? And here, if we say r the remainder, we should have the degree of r should be strictly less than the degree of the quotient. The degree of the denominator. It's not quotient. This is denominator. This is quotient. This is remainder. Well, it's just a name. Okay, so if A is a zero of P of Z, then we know that P of A is equal to 0, and P of Z can be written as Z minus A times let's say P1 of Z, where P1 of Z is another polynomial, is a polynomial, again, polynomial function. Right? So at this moment, we don't know if P1 of A is 0 or not. Maybe if P1 of A is 0 also, then we have P2. Then there is a polynomial function P2 of Z such that P1 of Z is Z minus A times P2 by the same reason. And if you do substitution, you will have the P of Z equal to Z minus A squared P2 of Z. Of course, we can repeat this process as further as possible. So eventually, there is a polynomial function pk of Z such that first pk of A is not equal to 0. You have to stop. And P of Z is equal to Z minus A to kth power times pk of Z. Right? So we push. This is the final step. You can push further. Okay, and here this k, of course, should k should be less than or equal to here. K should be greater than or equal to 1 and less than or equal to the degree of the polynomial, original polynomial P. All right, and you can say this is a multiplicity of 0, A of the 0A. correct? Okay, so in order to generalize this, we have the following definition. The definition is the following. You see, here is a polynomial, here's another polynomial. If f from G to C is analytic, and A in G satisfies f A is equal to 0. Okay, so you see, you have an analytic function, like you have a polynomial, and A is a 0 of a polynomial. You have the similar situation. Then A is a 0 of multiplicity m. Here m is greater than or equal to 1. If there is an analytic function like this pk of z from G to C such that f of z is equal to z minus a to power m. Here's m multiplicity m, and times g of z. So this one times another polynomial. Here we're talking about polynomial. So you have a polynomial and a polynomial. Here we're talking about analytic function. So here's analytic. Here this is g of z is also analytic. And the pk of a is not 0, where g of a is not equal to 0, right? So that's our multiplicity. So we can define this. All right, we can define this. So this is one similarity about the multiplicity of 0. Another thing we want to discuss is that for a polynomial p of z, you may have 1, 0. Assume you know the multiplicity is m1. You may have second 0, or you may have the kth 0 with multiplicity mk. And then you have a polynomial s of z. Okay? And the polynomial s of z, where s of z has no 0. S of z has no 0, because you cannot continue. If you continue, you just keep going, right? So this place we say s of z will stop. If it is stop, it means we want to know if we do have something which cannot be factored as a linear product. For example, if we talk about the real world, this polynomial does not have a real solution or real 0, right? It's like the protocol type of S of z. But we want to know, in the complex analysis, do we have the similar situation? So in a complex case, this will not happen. A polynomial with no 0 will not happen. So fundamental theorem of algebra says that S of z is a constant if a polynomial, let's make it clear. A polynomial S of z is a constant if S of z has no 0. If you cannot find a 0, then it's definitely a constant. Of course, it's non-zero constant. All right. So this is a fundamental theorem of algebra, and we are going to give a proof. We will show it. Or we will show this. Okay. After we show this, we will have this so-called complete factorization. So after showing this, we will have the complete factorization. The complete factorization. Complete factorization means all the polynomial is going to be a constant times z minus a1 up to z minus a n, where n is equal to the degree of the p. Z1 up to Zn, they can be repeated. It doesn't matter, I just say it's a product of linear terms. Okay, so we're going to prove this by the analytic functions. Well, to prove this one, we need a concept. And definition. An entire function. An entire function is a function which is defined and analytic in the whole complex plane. Okay, entire function. So it is defined over the whole complex plane and it's analytic. So entire function just means f is from C to C is analytic. From C to C analytic. The standard example will be exponential function, sine function, cosine function, because sine is what is sine? I don't quite remember what is sine. EIZ minus E negative IZ over 2. 2i. And the cosine EIZ plus E negative IZ. Yeah, I believe so. Okay, anyway. So sine and cosine are linear combination of a exponential function. Clearly, they are entire because z is entire. Z is entire. Okay, and we know that in the theorem 2.8, and the corollary 11 point and not 11. 2.11, corollary 2.11, the f of z is equal to sigma a n z minus a to nth power n from 0 to n with radius of convergence r. What is r? R is the distance between a and the boundary of G, boundary of the domain. But here, its domain is whole complex plane. Its boundary is infinity. So for entire function, f of z is always equal to the power series a n z minus a 7 for all z with radius of convergence infinity. Radius convergence infinite just means it is always convergent. All right, that's the best function. We don't worry about the convergence at all. Okay, so it's always a infinite degree polynomial, but it's different. And well, it's not different from polynomial. It share a similar property, not different. It's a share similar property about polynomial. The polynomial, okay, let's say a polynomial. Polynomial, for example, if it has coefficient, you just divide by the coefficient. So we assume the coefficient is, the leading coefficient is 1 plus a0 is a polynomial with degree n greater than or equal to 1. It's really a polynomial, not a constant function. Okay, then we factor out z to n. So you will get 1 plus a n minus 1 over z, a0 over z to n, like this, right? And then we calculate the limit at infinity. When z approaches infinity, p of z, this term, it will approach infinity. Modulus will approach infinity. This term will approach 0, All these terms will approach 0, but at 1 it approaches 1. So it's infinity times 1 is infinity. Okay, so from here we get what? A polynomial. It will approach infinity, so it means it's unbounded. A polynomial is bounded, then it is a constant function. Only a constant function can be a bounded polynomial. Only constant function can be a bounded polynomial. The proof is here, very clear. Right? Bounded polynomial is a constant function. Because if it's not a constant function, it will be unbounded. Then this property holds for the analytic function, for the entire function, because you have to allow z approach infinity for whatever direction. So it has to be defined and analytic over the whole complex plane. So the analog of this result is about entire function. So Liouville theorem. Liouville theorem says a similar stuff. If f is a bounded analytic function, bounded entire function, then f is constant. But this proof is quite difficult, more difficult than this simple calculus proof. Okay? It has to be bounded, it has to be entire. Of course, we have a lot of function bounded, analytic, but it's not entire. All right? Okay, it's bounded, so assume f of z modulus less than or equal to m for all z in C. It's bounded. Okay. We're going to show it's a constant. We show that f prime of z is 0 for all z in C. We will show this one. This will imply f is a constant function. Okay, so f is analytic. So f is bounded. Entire means it's analytic over the any disk. So f is analytic in whatever disk centered at whatever point with whatever radius. Okay? Okay, then remember that the Cauchy estimate. This is a Cauchy estimate. By Cauchy estimate, we're talking about the first degree, first derivative. So we have n equal to 1. So f prime of a is going to be less than or equal to n factorial is 1. M is here, m. R to n, r. So be careful, this m is fixed, this r is whatever r. So here, r is arbitrary. Positive. Arbitrarily positive. And positive. Arbitrary and positive. So let r approach infinity. Okay, let r approach infinity, we have the modulus f prime of a is less than or equal to 0, because m over infinity is 0. Right? It's less than or equal to 0, so it's equivalent to f prime of a is equal to 0 for all a in C. Here we even don't care to pick up the a because it's entire function, it's analytic every place. Okay, f prime of a is 0 for all a in C, so f prime of z is 0 for all z in C, so f is a constant. So we are done. This is Liouville theorem. Liouville theorem says bounded entire function must be a constant function. Bounded entire imply the constant. All right? Bounded entire imply a constant. Okay, so with the help of the Liouville theorem, let's try to prove the fundamental theorem of algebra. Fundamental theorem of algebra. So if P is a non-constant polynomial, then there is a complex number A with P of A equal to 0. So it just says non-constant polynomial must have a 0. Non-constant polynomial must have 0. Okay? Non-constant polynomial must have 0. It's not like the real one. The real one, for example, x squared plus 4. It's a non-constant real polynomial. It does not have real 0. Here it has a complex 0. Always have complex 0. Right? Okay, that's proof. If I have some strategy to find a 0, that's called constructive proof. Unfortunately, there's no such proof. So if you cannot directly find it, you are going to prove it by contradiction, which means if it does not have a 0, what property will be broken, right? So we prove it by contradiction. Assume that P of z is not equal to 0 for all z in C. We prove it by contradiction. It's not equal to 0, we can put them on the denominator. We cannot put it on denominator automatically because I don't know if it can be 0 or not. Okay, so this implies f of z is an entire function. Why it's entire? P of z is a polynomial, is defined everywhere, and for every point is not equal to 0, you flip it, it still makes sense. It's still analytic because we have the quotient rule, right? So this is an entire function. Entire function. Let's see. P is non-constant. P is non-constant, then we already showed that the limit z approaches infinity, P of z will be infinity. Okay, here this infinity means the magnitude will approach infinity. All right, if the magnitude approaches infinity, 1 over infinity is 0, so the limit z approaches infinity, f of z, which is the limit z approaches infinity, 1 over p of z, 1 over infinity is 0. This makes sense. Each of the denominator is now 0, but they will becomes bigger and bigger when z becomes infinite, approaches infinity. So the reciprocal is 0. Okay. The reciprocal is 0. Well, let's see. F at infinity is 0. What does it mean? It means when z is sufficiently large, it will be close to 0. So let's say, given epsilon greater than 0, there is capital, do we have capital R? Yeah, there is a capital R greater than 0 such that for all z modulus greater than capital R, f of z modulus will be less than epsilon. Close to, it's minus 0 is less than epsilon. Let me rewrite. F of z minus minus the limit is less than epsilon. All right, so choose this r equal, choose this epsilon equal to 1. Then there is an r1 greater than 0. We just repeat this by selecting this special one, such that for all z modulus greater than r1, f of z minus 0, I don't write it, it's less than 1. It's less than 1, right? Okay, so outside the disk, this means outside the disk centered at the origin with radius r1. The modulus is less than 1. The B0 R1 closure is a compact set, right? Closed bounded set. Closed bounded disk is compact. It's compact set F. F is an entire, of course F is continuous. F is bounded on B0 R1 closure. All the continuous function are bounded over the compact set. And it is also less than 1, where is it? Less than 1 when it's outside. So say, let's make it concrete. Say it is less than or equal to m for all z in B0 R1 closure. Okay, so inside the closed disk, modulus of f of z is always less than m. Outside of the closed disk, f of z modulus is less than or equal to 1. Hence, modulus of f of z is always less than m plus 1 for all z in C. Inside dominated by m, outside dominated by 1. So it's always correct. What do we get? We get f is bounded. F is bounded. F is entire. By Liouville theorem, f of z is constant. Bounded entire function must be a constant function. So f of z constant. F of z constant, f is just reciprocal of p. Hence, p of z is constant. Constant, contradiction, right? We know it's non-constant. Contradiction, no. So the contradiction comes from your assumption p of z is not equal to 0 for all z, which means that the well-definedness of f. If this function is not well-defined at all, you don't have such argument. All right, so we finished the proof of a fundamental theorem of algebra. Every non-constant polynomial must have a complex solution. Non-constant polynomial must have complex solution. A complex solution. Right? And once you have this fundamental theorem of algebra, we can write that complete factorization. So we will have if p of z is, this is corollary, if p of z is a polynomial and a1, am are its zeros with multiplicity, aj having multiplicity kj, then p of z can be written as a leading coefficient c times z minus a1 to the power k1, z minus am to the power km for some constant c, and we should know that the multiplicity, the sum of multiplicity is equal to the degree of p, is equal to the degree of p. Okay, so this is the complete factorization. All right. Okay, excellent. So we first quickly, it's well, even though I said quickly, we didn't skip anything. We present all the necessary steps, but still, it's a very good idea to do all these stuffs, and you borrow a big theory of analytic functions, so you can prove this fundamental theorem of algebra in such an easy way. You see here it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines to prove this so famous theorem. Okay, go over all the process and get the idea clear. All the stuffs come from that integral representation f of z. All the stuff come from that, because of that stuff we have the power series and the stuff and the rest of them. Okay, we finish this video and we will continue in the next video. Thank you very much.